Hello guys, my voice audible to you?
Yes, sir.
So we have seen the parallel plate capacitor and its multiple varieties. So we filled with different types of dielectric, and we also obtained different combination. And we saw two methods. One was the very raw method in which we tried to derive through the basic. The other was the circuit method in which we converted this combination of dielectric into uh, series and parallel grouping of capacitors. And using the idea of grouping, we got the equivalent value of C as well as equivalent value of K. So after all this, we can now will go to one of the concept which is mostly forgotten and not mentioned in most of the textbook. So to understand that concept, we'll take the example of again parallel plate capacitor, which is filled with exactly two dielectric, half each. So now you can see these are two dielectrics which is kept between the plate of a different dielectric constant K1 and K2. And one of the plate is given a charge plus Q, yes, called plus Q, and the other is given a charge called minus Q. So now the moment you give charge plus Q and minus Q to the plates of capacitor, the obvious question is what will be the electric field the plate will create? Assuming area to be the electric field developed by the plate is how much? Anyone? A plate having charge Q will generate an electric field. I mean, this capacitor will generate the electric field of what value? I would say plates. It means the combination of left and the right plate. So what is the electric field between the plate of capacitor? Electric field between the plates of capacitor is how much? What was the formula? Tell me guys, anyone? Hello, hello. Am I audible? Are you guys there? Anyone? Hello, hello, hello. Hello everyone, am I audible to you? What?
Yes.
Why everyone silent? Adit, Harchit, Atharv, Garv, Harshit, Kanu.
Sir,
Am
you're
I
audible.
audible?
Yes.
If I'm audible, then why not replying? What is this? So what is the electric field due to the plates? If we have simply a parallel plate capacitor, and if one of the plate is positively charged, and other is negatively charged, what is the electric field between them? The E is how much?
Sigma by epsilon.
Very good. So why not all are responding? Like, are you forgotten everything so far? Really sad. So the electric field developed by the plate is sigma by epsilon, or you can say E equals to Q by A epsilon. The revised capacitor properly. I think you are forgetting everything. And in case if you don't remember, you can derive it using the Gauss law. Now you need to remember that how to derive using the Gauss law. So none of you have practiced anything like this. Really sad. So the plate will create this field, which is sigma by epsilon, which is Q by epsilon. But the moment you enter the first medium, the field will become, if I call E plate as, let's call E, which
By
is
K1.
by K1. So the electric will become E by K1,
Yes.
but here it will become E by K2.
K2.
So now the question is how the field will change suddenly. While going forward, how the field can change. Who will change the field then? I mean, there should be someone who is changing the field, isn't it? So there comes the idea of charge on the interface. Whenever we have two dielectric, and if this is the interface, then what you don't remember is that at the interface, the field changes abruptly due to some charge appearing on the interface, which we generally don't show. But the charge density on the surface of the interface, let's call sigma I be the surface charge density at interface. So if sigma I be the surface charge density at interface, in that case, again we can find that charge using the Gauss law, because we know that the charge only appears at the edge of a dielectric. It never appears in the bulk, because the bulk charges are compensated. So some charge will be here, some charge will be here, but together we have single value, which is sigma. So if sigma is the resultant surface charge density, if sigma is the resultant surface charge density, in that case, we can find the flux. So if I choose this area as, let's call this area as A dash, what is the flux, or what is the going to be the flux through this cylindrical Gaussian surface? So the flux through the cylindrical Gaussian surface is how much? So if you write the flux definition E dot dA, so from the left, the electric field lines are entering the cylinder, isn't it?
Yes.
So lines of force are entering from the left side. And the same lines of force will exit with a different value from the right side. So what is the total flux to the cylinder? Tell me. Total flux through the cylindrical Gaussian surface is how much? So the field which is on the left side is E by K1. And because it is entering, so it is a negative flux.
Negative.
E by K1 into A dash is the negative flux. What is the positive flux?
E by K2.
And what is the charge enclosed by the cylinder? The charge enclosed will be near the cross section, near the interface of the cross section, you can say. So the charge enclosed is sigma I into A dash upon epsilon naught. And therefore, E into 1 by K2 so the interface surface charge density will be epsilon naught into E epsilon into E into 1 by K2 minus 1 by K1. And we know from the above question that epsilon naught into E must be equals to sigma, which is the actual surface charge density of the plate. So sigma is sigma plate 1 by K2 minus 1 by K1. And depending on the K2 and K1, the sigma I can be positive, can be negative. So the interface may have a positive charge, may have a negative charge, that this equation will decide. It is clear. What you need to understand that whenever there is a change of medium, whenever there is an electric field, there must be some induced charge on the interface, which will result into the change of the net field on the two sides of the interface. So that is something very deep and very advanced. And you may expect questions like this in JEE Advanced. So as a thumb rule, what you need to remember is that whenever there is a change of medium, change of interface, they say when you enter from plate to the dielectric, that is first change. Then you enter from one dielectric to another dielectric, which is the second change. Then you go from the second dielectric to the air, which is third. Then air, like it's, you can say from second dielectric to plate dielectric. There are three changes you can see: plate, dielectric one, dielectric two, plate. And every change will have the charge induced. So whenever we have the change of interface, there is always a charge induced on the interface. This is thumb rule. And that is how precisely the law of refraction works. So light itself is oscillating electric and magnetic field, which you don't know as of now. So light is an electromagnetic wave which carries electric and magnetic field both. So whenever you go from one medium to another medium, because mediums are nothing but dielectric. So whenever you go from one medium to another medium, the electric field of the light near the interface will abruptly change on the other side because of the induced charge on the interface. Now, because this happens dynamically, so the behavior is quite complex, not easy to understand at the level of JEE, but definitely beyond the JEE level, at graduation level, it's not a big deal. It's a simple concept taught in at every university. So it is the induced charge which is affecting the field, and because the resultant electric field will change in its direction because of the induction process, that is the reason the light will bend while crossing the medium. When you say two medium having the similar refractive index, it means you are saying that they are same dielectric and therefore they are having the similar electrical and magnetic properties. So in a way, they don't change. It means there is no interface concept when the medium is continuous. Only when there is a change of medium, the induction will take place and the field will change, which in turn bend the light. That is the actual cause behind the bending of light. And what you call the refractive index itself is depending on the variety of electrical properties like charge density of the medium, induced dipole moment, oscillation frequency of the electric field of light, and so many other things. So at a very advanced level, you will see that the mu is a function of multiple variables, and it is 1 plus something. There is a formula of mu, which is 1 plus something. A big complex relation is there. So that is why the mu is always more than 1, because it is 1 plus something positive number. So you will see later on, maybe if you pursue the physics at higher level, you will come to know. So as a thumb rule, remember this, and this is not only for the dielectric, even when we study about the conductors, which is the next chapter. And when you go from, let's say, if I join two conductors, let's say one is aluminum, other is copper. And if I put a battery or a cell across the two conductor, because the current will flow in the two different medium, and there is an interface, which is the end of aluminum and the beginning of copper, even that interface will develop some charge, and the charge will be responsible for changing the field on the two media. So the thumb rule is simple. Like whenever you have the change of medium, whether it's conducting medium, whether it's a dielectric medium, the change will always make the induction process. Okay. So this is something that you should remember. Questions can be asked. So I think we are done with the parallel plate capacitor. So we should go to the other shape of capacitor, which we should be interested. So we'll start with the other plate, which is like a spherical plate capacitor. Have you done the spherical plate before?
No.
So spherical plate. And probably now you need to recall the method of finding the capacitance, the steps that we mentioned earlier. So in a parallel plate capacitor, by default, you give one charge plus Q to the inner surface and minus Q to the other surface. So if you give plus Q to this and minus Q to this, the other way of saying is either you do this, or what else you can do is you can give a charge Q to this and just ground out. We have done the grounding in the past, right? In the electrostatics. Yes or no?
Yes.
So when we have conductors and when you give charge to conductors, what will happen? It will undergo the redistribution. It will undergo some sort of induction. So once you give charge to the inner surface, a positive charge layer will appear here, and a negative charge layer will appear here. And because minus has already appeared in the inner surface, the outer will have no charge, isn't it?
Yes.
The same situation is here. If you give plus Q, this will have the plus charge here, and the minus will appear here as a result of induction. Now the outer surface is given no charge, so plus Q might have appeared on this side, but because of grounding, all of the charge will here go to ground and it will become 0. So we have discussed this. If you have forgotten, go and rewatch the video. That's good for you. So now we have two spherical shell, and let's call the radii of the shell, inner shell as A and outer shell as B. Now, as a practice, you can remember that whenever we try to derive the capacitance of a system of conductors between the terminals, so here we have the inner shell and outer shell as two terminals. Either you give plus Q and minus Q, or you give plus Q to the one and ground the other, which will be having similar effect. So the next step is the way we define the capacitance is it is the amount of charge given to a conductor and the rising potential, right?
Yes.
So if I choose the outer as grounded, which is the reference, the inner potential, if I call V, then the potential difference will be same as the potential of the inner surface, isn't it?
Yes.
So delta V is equal to V here, which is the V inner. V is the potential of the inner surface. V is the potential of inner surface. So generally we look for the difference, but luckily if I ground one of them, then the potential itself is the potential difference. Is this clear?
Yes.
So potential difference between the two shell is the potential of the inner shell, because outer is zero. So anything with respect to zero is the difference itself. So now to find the potential difference, you can use either Gauss law, and you can use the definition of delta V, which is minus E dot dr. Or because of the spherical nature of a shell, we know the potential of a spherical shell. From electrostatics, you can find the potential of the inner shell because of the all charge distribution. So you can do by both the methods. So which method do you remember, guys? Tell me. Do you remember anything? Or
Okay.
forgot? I have forgotten everything. Tell me. Be honest. How many of you have forgotten completely electrostatics and Gauss law? Raise your hand. It's okay to accept, then hide and pretend that you know everything. Raise your hand if you have forgotten. It's totally okay. So you all remember the potential formula? I can ask anyone randomly. If you don't raise your hand, I will ask. So how many of you don't remember any formula of potential? Okay, so you all know? You all know the formula for potential? Yes or no?
Yes.
Anyone who doesn't know, you can raise your hand. I will not ask. Okay. So you all remember? All right. So who will answer? Yeah, Harshit, tell me. What is the potential difference between these two shells? Or what is the potential of the inner shell? Tell me. V equals to Harshit, are you there? Hello, guys. If you don't respond, it's really bad thing. Don't disappoint me. Who will tell? Anyone interested in telling the answer? Or all want the answer only? Watching it like a video?
Sir,
Yes.
sir, it will be like the U potential of self plus potential of mutual. So like that
No,
only.
I'm not asking potential, I'm asking potential. So probably you also don't remember what is potential, what is potential energy. Revise it, everyone. So do one thing. So I'll pause the video, open your notes, see all the formula, and respond back to me in 10 minutes. I'm pausing the video. Yes, Mukta, tell me.
KQ 1 by A minus 1 by B.
Correct. So potential of the inner shell is KQ by A because of its own charge, and minus KQ by B because of the other charge. And because this is the potential of inner shell, outer is at zero potential, therefore the potential difference is this much itself. So we got the delta V as Q by 4 pi epsilon naught 1 by A minus 1 by. And therefore the capacitance equals to So by definition, we have know it's Q by delta V, which can write as Q by 4 pi epsilon naught. Q gets cancelled, so C becomes. Now, can you do it by the Gauss law and using this relation, or integrate from A to B? So, what is the electric field at a general distance r from the center of the shell? Tell me. What is the electric field? Tell me, guys.
Q by 4. Hello.
Yes.
Q by 4 pi r square epsilon.
Q by 4 pi r square. Absolutely not, right? Q by 4 pi epsilon, like this or like this? Where? The r square is in the denominator or in the numerator?
Upon denominator.
Upon. Very good. So you know the electric field, then you can write this dr, because the angle between the E and dr is
0.
0. And then you integrate from where to where? A to
A to B.
B. And what you need is just a value. Oh, now we can add this.
We'll get this.
Yeah, just take a value. So the answer will be how much?
Q by 4 pi epsilon naught 1 by minus 1 that.
So no matter which form you choose, the first form is easier for concentric shell, but in general you should know the Gauss law. And now because you know the potential difference, the method remains same. So this part is same for all, right? Now delta V you can calculate as per the situation. So do revise the Gauss law. It seems like you all have forgotten almost all of the electrostatics, which is not a good sign for your preparation. If you really want to master the chapter of any chapter of class 12, whether it is electrostatics, capacitor, electricity, magnetism, EMI, AC, your Gauss law will remain intact everywhere. So you have to use Gauss law not only in this chapter but in other chapter as well. So in case if you are not able to recall, keep on revising. It's very important. In this case, there is one more variant that we should be aware of. And that is capacitance of solid spherical conductor. So what if I give you a pure conductor of radius r, okay? So if I give a charge q, what will be the potential of the surface? Tell me, guys. So in case of conductor, what happens? The charge given will reside on the surface itself. So what is the potential of surface? Am I audible or not?
Q by 4 pi r square epsilon. Hello.
Yes.
Q by 4 pi r square epsilon naught.
Is it the formula for potential? Are you sure?
No. I heard electric field. Sorry, sir.
Hmm.
So
So what is the formula then?
KQ by R.
KQ by R, which means Q by
4 pi epsilon naught R.
So now if the plus plate is here, where is the minus plate? If there is no field line, I mean, there is no next shell given to you, but we can always assume infinity as the termination. Because every field lines will eventually terminate at infinity, isn't it?
Yeah.
So every field lines will terminate at infinity. Every field lines will terminate at infinity. And if every field lines will terminate at infinity, then the infinity will act as the hypothetical shell. And what is the distance now for this shell from the center? The distance is infinite, right?
Yes.
So what is the formula for capacitance? So potential difference is how much? This is zero potential. So potential difference itself is the potential of the inner surface.
Yes.
So by definition, C equals to Q by delta V, but delta V itself is V. So the answer becomes 4 pi epsilon naught R. So capacitance of a conductor is, and what is really interesting that the C is directly proportional to radius. So for any spherical conductor, isolated conductor, the capacitance is always proportional to its radius. Is this clear?
Yes.
Okay. The other way of deriving is we have the formula for spherical capacitor. We know the answer is 4 pi epsilon naught 1 by A minus 1 by B. And if you use the formula, you can write as 1 by R, well, that's A, and B is infinity, which is a similar answer. So for every spherical conductor, the capacitance is proportional to R. Is this clear?
Yes.
Okay. So charging and discharging of spherical conductors, what we need to remember. So if I bring two conductors of different size, let me change the color as well. And if the first one will have the radius, let's call R1, the radius, let's call R2. And now we have a conducting wire with a switch. And the first of the conductor is given a charge, let's say Q1. So what is the potential of the first wire? First conductor potential of the surface is
K
Q1 by
4
pi epsilon.
4 pi epsilon naught R1, right? And
Yes.
what is V2?
Q2 by 4 pi epsilon naught R.
Very. So Obviously, I mean, we have no idea what is happening. We don't know the ratio of Q1 by R1, Q2 by R2. So if Q1 by R1 is more than Q2 by R2, then which one is at high potential? The first, right?
Yes.
And vice versa, then second. And if both are equal, then there is no difference.
Yeah.
So when charge will flow? Only when there is a difference, isn't it?
Yes.
So what difference will allow the charge to flow? It is the potential difference. So what we need to remember that it is the potential difference that will result into flow of charge. And if potentials are equal, then there is no flow of charge. Is this clear?
Yes.
So let's take a scenario. I mean, because we have to solve this question, so we have to choose one of the condition. So if I say that Q1 is Q1 by R1, sorry, Q1 by R1 is more than Q2 by R2, okay, then definitely the V1 is at high potential than V2, right?
Yes.
So let V1 is more than V2 because we want to solve the question, and switch SW is closed now. So the moment you close it, let me draw it quickly. The moment you close it and you have established the path, so this is like a connecting path which will allow the charge to move across, and therefore, because I have taken V1 as more than V2, so some charge of Q1 will go to Q2. So the charge left will be here, Q1 minus Q. And what is the charge here?
Q2 plus.
And now the whole idea is that the flow will eventually stop when they acquire the same potential, isn't it?
Yes.
So what you are supposed to write, and we have to also assume the distance between them is far enough not to interact with anyone. So here the assumption is, assume the spheres are far away from each other. Technically, there is no interaction happening. So now what you are supposed to write is at equilibrium, what must be same? Tell me, guys.
Potential.
So what should I write here? If it is same, if you know the
V1 should
potential
be
same,
equal to V2.
what is the formula for that?
Q minus Q by 4 pi epsilon naught R1.
Equals to,
Q2 plus Q upon 4 pi epsilon naught R2.
you can see 4 pi will cancel out. In fact, this is what you're writing is the Q by C. And that is the potential for the capacitor. It is Q by C, the capacitance, isn't it? So this is same as writing by C1 by C. Because 4 pi epsilon naught R1 is capacitance, if you remember. And for any capacitor with charge Q, the potential difference is Q by C. I hope you remember.
Yes.
So now by solving this, you can easily get the charge which has flown. So technically they'll ask you the charge flow. So R2 Q1 minus Q R2 is R1 Q2 plus Q R1, and therefore R2 Q1 minus R1 Q2 is Q into R1 plus R2. So you can exactly calculate how much charge can flow, isn't it? So what we are getting? Let's see once again. R2 Q1. Are you guys writing along with me?
Yes, sir.
Yeah. Whenever I derive, you all must write. Don't wait and see as a like some movies going on. And if you do so, it will harm you really bad. So the only way to learn is to write and learn. Don't watch and learn. Okay. So we got Q equals to how much? R2 Q1. And this we can write in a nice form by dividing R1 R2. We got Q1 by R1, Q2 by R2. So we are dividing the numerator as well as the denominator by R1 R2. I hope this is clear.
Yes.
And if I want to convert this into uh, capacitance formula, so what I will do is I can only multiply with 4 pi epsilon not everywhere, right? If I multiply here, if I multiply here, if I multiply here, because it will not affect the overall answer, isn't it?
Yes.
So this will look like, so what I'll do, I'll do this in the next step. Okay. Or we can write like this, because C is 4 pi epsilon naught R. So 1 by R is 4 pi epsilon naught by C. This is also easy way to substitute. So it is up to you the way you want. So okay, I'll just convert this into. So Q1 by R1 is okay, like 4 pi epsilon naught R1. Q2 by R2 we can add is 4 pi epsilon naught R2 upon 1 by 4 pi epsilon naught R2, 1 by 4 pi epsilon naught R1. And so what it becomes Q1 by C1 minus Q2 by C2 upon 1 by C2. I can, okay, 1 by C2 plus 1 by C1, which we can rewrite as Q1 by C1 minus Q2 by, and this is like 1 by C1 plus 1 by C2. Okay. So the final answer you can remember is Q by C1 is called V1. So the potential of each sphere, and 1 by C1 plus 1 by C2 I can assume as something like 1 by C equivalent of series combination. Imagine these two are in series. So Q turns out to be how much? So now, for exam point of view, this is the formula that one should directly remember to get the charge flow without doing all the rigorous calculation. It is very simple. It is a C equivalent, assuming where
It is in series, right?
assuming it is in series, where C equivalent is
like for the formula, we
yeah,
assume it in series.
correct.
Okay.
So where C equivalent is equivalent capacitance, assuming to be kept in series combination. Understood?
Yes.
Yeah.
So 1 by C equivalent is 1 by Cm plus 1 by. So let's do some problem just for practice. So the way it will be given to you is not in terms of capacitance. They just give you sphere. And to make it simple in terms of calculation, I'll take two sphere, one with radius r, another with radius 2r. So for what value of charge relation, the potential will be same on both. So if I choose a charge capital Q here, what should we choose here to make the potential same?
By 2.
2Q.
Two.
Because the potential we check as a Q by R ratio, right?
Yeah.
So by making the charge in this ratio, we can have the potential same. So now let's say if I give equal charge to both of them, then which one is at high potential now? So which one is at high potential? Tell me.
First small.
Very good. The first one is at high potential. So the moment I connect and we have a switch which we can close, we can directly tell that how much charge will flow. So what is the C equivalent? 1 by C equivalent is 1 by C1, which is 4 pi epsilon naught R. 1 by C2 is 4 pi epsilon naught 2R. So I can take like 1 by 4 pi epsilon naught. Just a moment. Okay, so this is the easy way of writing. You can add everything in terms of K, where K is 1 by 4 pi epsilon naught, because that's very common thing. So the Q by formula was what? C equivalent into high minus low.
Yeah.
So we only write high minus low because we want the flow from high to low. So the answer is 2R by 3K. 2R by 3K.
Q by 3. Sir,
Tell me.
sir, we can directly use the formula of radius, right? Like Q
Yeah,
and
yeah.
radius.
Yes, definitely can use. So this is easy to remember. That's it. But to solve, we can use the basic also. That is always better. Instead of doing all these things, what you can do is,
We can directly get.
yeah, you can directly assume that, okay, let's say Q minus Q by R is Q plus Q by 2R. That's it. This will give you
Yes.
in one line. Yes. Very good. So that is the basic one. That is how we derive everything. So now this will give you the answer directly. Q minus Q equals to Q plus Q, and therefore Q is 3Q and Q is. So many of you got the answer using this, which is the method. Okay. So now the next question that they will ask you is if you know the new charge distribution. So if I say this is the continuation of okay, I will tell you when this is useful. This is only useful when they give generally potential instead of charge or radius. Yeah. So if they give you potential only, let's say 10 volt, 20 volt, if they don't mention about the radius, you can go by this method. And then they will give you the capacitance. So in the context, you have to understand that which one is the best way to approach. So continuation of previous problem. So we have the new charge distribution. What is the new charge distribution? Q minus Q by 3.
Yes.
And Q plus,
Plus Q.
yeah, Q by 3. So we have here 2Q by 3 and here. Now you can see clearly the charge on one is double the charge of other, right?
Yes.
So with new distribution of charge, the overall energy of the system will change. If you try to understand, the charge has changed on the two sphere after this connection. So this is the after scenario. For comparison, we can do the other scenario. So before it was how much when it was open? So when this was open, the charge was Q and Q. So can you find the total energy of system, assuming only self energy because they are not interacting. So what is the U initial? So we know the self energy of each sphere, what the formula is, how much?
2 by 3.
The formula is KQ square by 2R.
Self. Okay.
Self. For a hollow shell, right? Because the charge is only on the surface, no?
Yes.
So it is not a solid, it's a hollow shell.
Hollow.
So I'll write the potential energy one by one, side by side. So for the LHS, let me write the final one. What is the answer? K Q square by 2R plus K Q square by 2R, ignoring mutual interaction. So if we are ignoring the mutual interaction, if we are assuming they are far apart, then this is the. And if you want to add the mutual interaction, it will become K Q and Q2 by. I need to give the separation. Let's say D, something like that. So if separation is not given, it means they do not expect the interaction energy. What they expect is only the self energy, and that will be evident from the question. Understood?
Yes.
So they will give you, okay, the two spheres are at D separation. If they are giving you the separation, it means they expect you to write the mutual potential as well, which is not a difficult task. You have to just write one more step. K, Q1, Q2 by separation. I hope this is clear.
Yes.
So this turns out to be, we can take common KQ square by 2R as common. And this is 4 by 9 by 2, which is 2 by 9. And this is 2R is common. Oh, sorry, this is 4 by 9 only. So K by KQ square by 2R is common, and 4 by 9 plus what is here? 16 by 9, 8 by 9.
16 by.
Correct?
Yes.
Because these two will cancel out, right? So what we are left with is 12 by 9, which is
4 by
3, 4, 4 by 3, right? 4 by 3, 2 by 3, 2
2
by
by
3.
3.
And what was the initial value? Do the same trick. KQ square by 2R plus KQ square by 2 of 2R. You can take common, and this is 1 plus 1 by 2, which is 3 by 2. So this is 3 by 4. Am I correct?
Yes.
Now tell me which energy is more, the initial or the final? Initially is 2/3, now it is 3/4. So it is from 67% to 75%, right?
Yes.
So initially it was
Initially.
something 75, now it is 67. So the energy has been lost.
Yes.
Now they will ask you where the energy got lost. So when the charge will flow through the wire will dissipate as a heat. Okay, so they will ask you how much energy has been dissipated through the wire, through the connecting wire. So whether I mention a resistance or not, the heat will dissipate through the wire, and the amount of heat dissipation has nothing to do with the resistance. Why? Because resistance can control the flow of rate of flow of charge, but resistance will not decide how much eventually I will lose it. So whether I mention the resistance or not, the wire will always dissipate the heat, and that will be the biggest discussion of the next chapter called RC circuit. So the question they will ask you, what is the heat dissipation? So in the process, there is some dissipation in the process. And we can attach it delta Q, or that looks bad. So for delta H, the amount of heat dissipation will be initial minus final, because we are at the value, which is 3 by 4 minus 2 by 3. How much is that? 1 by 12.
1 by 12.
So the answer is KQ square by 12R. Understood?
Yes, sir.
So this is the heat dissipation problem that they ask, and this you can do indirectly like this. So every question of capacitor, if it's belonging to the spherical, you can solve by the idea of electrostatics. If it is not spherical, then the only way is to use the capacitance as a circuit idea. And that is why this question you can either see in some book, some textbook with this, they put this problem in the chapter of electrostatics, some put it in the chapter of capacitor. The choice is yours. It really doesn't matter. So this can be analyzed in two ways. We'll see in the future what are the other ways of writing. And every question that we solve, again, I'm saying every question that I solve in lecture, you're supposed to derive till you get it right. So if you think that, okay, the lecture is only to watch and you will solve the unsolved problem of the book, you will never learn physics. Always practice the class problem first, master the class problem, and then only attempt. Because if you do so, 70% of your problem in any book will be solved by that time. Because I take care of every problem written anywhere which is pertaining to JEE syllabus. Okay. So after the spherical capacitor, we'll move towards something called cylindrical capacitor. There's one more problem. Okay, I will give that. Have I shared the sheet with you guys? The electrostatic sheet?
Electrostatics.
Yes or no?
Yes.
Yes.
Okay. So I think where can I get? Even I don't. Okay. But oh, I think capacitance. Just a minute. I think I haven't shared the capacitance, right?
No.
No.
So happy, no? At least you don't have any burden of solving. Okay, anyway, let me share it to take away your happiness. So you all can open it and come to page number 15. Page number 15.
Yeah.
Okay.
Match the column.
No, question number 5. Page 15. 15.
Okay,
It's
so
it's below that. Below that.
yeah, got it.
Yes.
You can see question number 4 and question number 5 both, right?
Yeah.
So start with
Yeah.
question number 4 and then solve 5. Okay, everyone, practice this. I think fourth question is done. So whenever you have two conducting shell and if you connect it, what will happen? No charge can reside inside the shell. We have done this question.
Yes, sir. It'll be
Yes, sir.
outside.
So actually it is not two shell, it is just only one shell.
Yeah.
And so the answer will be for only outer shell.
Outer.
Yeah.
So which option is correct?
Option
Option
C.
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 That's it. So C is the answer. So when whatever charge you give, it will only appear on the outer surface, outermost surface, I would say. And that will get only one capacitor, one single spherical capacitor, which is having value 4 pi epsilon naught R, which is R2 here. And
R2, yeah.
so C is the answer. Now think of the fifth question. How you are going to approach question number 5? Tell me the approach only. I mean, don't solve. Just tell me the approach. Anyone. If you have any idea. You read the question and tell me the approach.
Sir, here first we need to find the potential.
Of each
Yeah, and yes.
and
And plus the mutual also.
yeah, of course. I mean, potential of everyone,
Yes.
your and others, and then take the difference.
Yes.
And note the first step. You give plus charge to one of them and minus to other.
Yes.
So the whole trick is take one sphere with plus charge, other with minus charge. Find the potential of each, take a difference, and then take the ratio of Q by delta V. That is the approach for every new problem which you come across. The approach to solve is same. So now we have two spherical shell, and they're looking for the. Now it is written that D is much bigger than A and B. What does it mean? That the charge distribution will be spherical on them. It is not going to be disturbed. That is why you can assume the spherical charge distribution for both of the sphere. It doesn't mean that you're not supposed to take the D. The D should be taken. So mutual should be taken. The potential of one sphere on the other must be taken. So try this out. Just follow the basic, you will get the answer. Everyone.
Sir, I didn't understand the importance of D much greater than A and B.
If it is very close, then due to the repulsion, the charge will or attraction charge will become non-uniform over the surface. Okay.
Okay, cool.
So if it is non-uniform, then it's difficult to write the mutual part. Okay.
Okay.
All right. Good question.
Sir,
Then okay. So which option is correct?
um, sir, D option.
D is I think A, B, C, D, right? D for Delhi.
Yes.
That's right answer. So Delhi is the right answer. Anyone getting D?
Yes, sir.
If you have got D, raise your hand. Those who have got the answer D, raise your hand.
Still solving. So 1 second.
Very good. Just follow the process.
Sir, in fifth question,
Hmm.
we have to also like we first give Q and minus Q. So okay, no, nothing.
So look at the question number 3. Those who have solved the question 5, and just tell me the answer. We have done this in class, I think. So for question number 3, what will be the answer?
It was infinity, right?
Right.
Yes, sir. I got.
Very good. And those who have solved both questions will not stop, will come down heavily, come down, and then there is a part 3, page number 21. Can you see page number 21? Page number
Yeah.
21.
Yes.
You can see the part 3.
Yeah.
Yeah.
Solve question number 1, 2, 3, 4, except the D part 4, and then come down. Okay, first you finish this.
So 1,
solve.
2, 3, and 4.
Yeah, 1, 2, and 3, 4.
Okay.
For 4, only solve the A and B part, because the energy part you have not studied, so leave this part. So solve A and B part, C and D part we'll see later on.
Okay.
I think question number 2 having some missing values. Question itself is missing. You can leave the question number 2, solve 1 and 3. So what is the answer for 1? It's very simple. You can orally tell me the answer.
Sir, same at B and C.
Very good. And what about A?
Yeah, 0 at A.
0.
Okay, very good. So if A will be 0 if the outer charge is 0, right?
Yes.
Yes.
But do we know that outer charge is 0 or not?
Charged parallel plate cover. So charges will be inside.
No, no. The charge distribution is not given, no?
Oh yeah.
Yes.
So in general, charge may appear at on the outer surface, right? In general.
Yes.
If you charge a capacitor using a cell or a battery, then only it appears on the inner. But if I give it externally, then it may appear on the outer. And therefore, I'm not sure about the A part. So it may be 0 or may not be 0. But what we can say for sure that at B and C, it must be equal. Why?
Same.
Because the
Same.
electric field is uniform.
Electric.
Yes.
Yes.
Okay, now solve the question 3. So what is the relationship between Q1, Q2, Q3, Q4? We know Q1 equals to, for any parallel plate capacitor, what we know?
Q4.
Very good. So Q1 and Q4 must be equal, isn't it?
Yeah.
Yes.
First you write all the possible
Q-
relation that you can see.
Q3 will be minus Q2.
Yeah. Q4.
Correct. Or vice versa. Correct.
Yes.
Very good. So 1, 2. So 1 equals to 4 that we know, and we know 2 equals to minus Q3 and vice versa. And now what they're asking, let's see the question one by one. The potential difference between the plate. So potential difference we write only in terms of. So potential difference, how we write Q by C. You can say Q2 by C or Q3 by C, because they are equal, right?
Yes.
Isn't it? So Q1, Q2 by C or Q3 by C,
Same.
same. And okay. So B and C are the right answers.
Correct answer.
Anything else? Let's check. A cannot be correct. Right? A is the charge on the first. Okay. So and D. Let's check D part. For D part, we have 1 by C. So A cannot be correct. Do you realize this? For the potential difference, what we see, we only look for the charge on the facing plate, isn't it?
Yes.
And they are equal in opposite. So if this is Q, this is minus Q, or vice versa. And therefore the potential difference is Q by C, which is same as Q2 by C, which is same as Q3 by C. So B and C are correct, A is incorrect. And I need to just check whether C, the D part is coming back to the problem on in the first case. So it's 1 plus 2 minus 3 minus 4 like this. 1 by C. It is 1 plus 4 plus Q2 minus.
This is also
Q3.
wrong.
Yeah,
Yes, sir. It is wrong.
just a moment. 1 plus, no, this is also correct. So this will also not qualify to be the potential difference. Let me just check the answer. Question number 3. Yeah, so B and C are the right answer. And those who have solved this B and C will come down to page number 27. Are you there?
Sir, the mains advanced questions.
Yeah, advanced question. And you can clearly see which question we have solved in the past. So you can solve question number 9 and 10.
Yeah.
Okay. So solve question number 9 and question number 10. And we have done all these questions, if you don't remember. Done, guys. Question number 14 and yeah,
But
9
10th
and 10.
one,
9 is done.
I'm not
Um,
getting
so
Anyone
9,
getting 9?
10.
so 9, I didn't go.
Why?
Um,
This is all are similar, like same method. In 9 we have two dialectic. We have done this question in class itself. So these two dialectic, one is air. If nothing is air, it means it is air, right?
yeah,
Yes.
For air, what is the K? 1.
1.
Do it. Try.
Hello.
Yes, tell me, tell me.
Sir, I'm not getting the 10th question. I got 9.
You got 9.
Sir, I
10th is
also
again
got
same. No?
9.
You have to just cut into pieces and make in series and parallel. You will get the answer. Okay.
Yes, sir, I got 9.
Yeah. And ninth we have solved. In fact, we have solved the ninth and 10th both in class. Let's check it out once again. Check
Okay.
the last I mean 2 lecture notes. You will get the answer. Do it again. Okay.
Yes, sir. I got the answer.
Okay, very good. So you got the answer, question?
Yeah, sir, we have to take four different. No?
Yes, not four different. You have to take the top layer. Just let me show you.
Sir, can you show?
Yes, yes. So parallel plate capacitor having plates say area S and plate separation D has a capacitance C1 in air. So the C1 is given, right? The air value is given to you. It's C1, right? So C1 for question number 10. The C1 can act as epsilon not A by D. Okay.
Yeah.
When two dielectrics of different relative permittivities are introduced between the two plates, as shown in the figure. So if you just draw the two-dimensional view, which is easy for you to understand, only one quarter is occupying a different value, right?
Yeah.
And the rest are different. So this is the simple diagram. I mean, why it is so difficult, I don't know. And now we have the terminal here. So you have to cut from between, right? From here. So A by 2 will have the combination of this and this. And this A by 2 will have only this completely.
So they both will be in series.
So the top two will be in series
Then parallel.
and then parallel with the bottom one. And you can add C1, C2, C3 is this. What is C1 here? Epsilon not. K is given how much? I think this is in the diagram
2
itself.
and 4.
E1, right?
Yeah. 2 is
So it is 2, no? Okay,
Yeah.
fine. So K epsilon not A by D, which is D by 2, right? So 2 epsilon not A by D. What is C2? Again, the other half, which is 3, I think. Four,
E2
four.
is 4.
4. So 4 epsilon not A by 2 by D by 2. Same. And what is C3? So C3 is epsilon not, which is I think 2 again. 2 epsilon not A by 2, but it's full D, right?
Yeah. Actually,
So we can take epsilon not A by D as some constant, C naught.
Yes.
So now the C equivalent is C1, C2 upon C1 plus C2 because they are in series in parallel with C3. So C equivalent is how much?
That is coming 4 by 3 absolute not A by D.
Yeah, so C1 is 2 C naught into C2 is 4 C naught upon 6 C naught plus C3 is a C naught. So 4 by 3, no? 7 by
final
3.
answer 4 by 7 by.
So this is the 7 by 3 C naught. And C naught is basically C1. So C equivalent upon C naught is,
7 by.
and probably this is what they're asking, right?
Yeah. Ratio.
The ratio. So the answer is D. And we have done this. Come on. How can you say you have not done this?
Yeah.
Which simply means none of you are revising electrostatics and capacitor. Okay, so this kind of reality check is necessary. So let's go back to the next one. So we can go for the cylindrical capacitor. So we have two concentric cylinders. Just so in case of cylindrical capacitor, first thing that you need to remember, irrespective of the diagram which I draw, the plate gap is very, very narrow. So A and B are very close to each other. And because the gap is very small, which means the field, this inner cylinder will act as infinite line charge. And therefore, you can also apply the electric field formula of the infinite line charge to solve this question. So you can take lambda as the linear charge density instead of sigma. So if I'm giving plus charge to the inner cylinder and minus to the outer, so definitely the field lines will be from the inner cylinder to the outer cylinder in the radial direction. That is the property of infinite cylinder, right? So field lines will be radially outward, isn't it?
Yeah.
And the similar here. But it is radial, which means as you go away, field lines will change, isn't it? I hope you remember this. So here, I mean, for cylinder, we cannot write for infinite line charge, we cannot write potential. So we can't do the similar thing that we did for a spherical capacitor. So here, the only way is to use the Gauss law to find the field and then use the E dot dr to find the potential difference. So, sorry. So you can take the length of cylinder as L, and what we take is lambda as the linear charge density, which is easy to express because the charge we can attach lambda into L. So can you find the delta V now
Yes.
using the
So
E dot
can
dr?
solve it.
Yes, please.
Hello.
Yeah, tell me.
Sir, I got the capacity.
Tell me. How much?
2 pi epsilon naught L upon log of V by.
Very. So those who have not put the delta V part, you can write as lambda by 2 pi epsilon naught R, right? Yeah. Just make it plus because we just want
Yes.
value. And R is from A to B. So lambda by 2 pi epsilon naught and dr value we can write as ln. And therefore the C is Q by delta V. And Q we can write as lambda L. Always try to do through the derivation and try to do the derivation as fast as possible. It is like it is just a formality of writing and getting answer. Understood?
Yes.
Done?
Yes.
Now this is a challenging problem. Not just challenging, I would say extremely challenging. It is a very famous question in history. That's called capitance of a telegraph wire. So the way to understand telegraph wire is it's basically two current carrying wires. So what you can think this as a two cylinders. So these are two infinite wires because the telegraph wires is spread across the city. So they are definitely very large in length. So to model this question, we convert this wire into two cylinders. So it is like finding the capacitance of two cylinder of unit length, or you can say it is a capacitance per unit length. So the radius of the cylinder is very, very small compared to the separation. So separation between them is D, and so you can imagine this as a uniformly charged cylinder. And And you can assume lambda as the linear charge density because the charge is infinite. So now assuming the same basic tactics, can you find the delta V? And as a thumb rule, the limit of integration will go from a to d minus a. We only go from here to here. So do the same method and tell me the what is delta V. Tell. So tell me delta V between the two center. Assume the length as L, and find the capacitance for the L length.
Hello.
Yes.
Will it be 2 pi epsilon naught L upon
Upon.
log of d minus a by a?
Yeah, that seems correct to me. But there is one thing which you might have missed. What is the electric field at a distance x from the center? This center. What is EP? So EP will be how much? We don't realize.
This I've missed.
So for one center it is x distance away. For other center it is d minus x away, and because one is plus, other is minus, so both will support in the same direction, right? So plus will create field this way, but minus will also create field this way.
Yes.
So the net field is sum of the two field. And now you can find the delta V by the same fashion. Simply write as the value will be how much? So the delta V turns out to be how much? and you can reverse the sign, it will add up. So what will get eventually this answer? Understood?
Yes.
So it will delta V turns out to be lambda by pi epsilon naught ln.
D minus C.
So by definition, capacitance will be Q by delta V. So we can take Q as a lambda into L because we are doing it for lambda L length of the wire. And delta V we got how much? So the C per unit length of the wire is
L.
so for telegraph wire we find the capacitance per unit length. We don't do it for the. Of course, we cannot do it for the entire wire, isn't it?
Yes.
So this is a basically famous question because every current carrying wire itself is a capacitor. So whenever we have two parallel wires running across, so they have capacitance also. So if you look at the transmission lines, then the two lines are actually capacitor, and they have the capacitance also. So they store electrical energy as well as they store magnetic energy both. Okay. It is clear.
Yes.
So similar to this, you can also solve a problem called capacitance of two tiny spheres. Which is very easy. If we have two spheres, and the distance between the sphere similar to what you just did, two sphere problem. So if I choose a radius as A and A, and the separation is, what is the capacitance of this combination? Can you think of the capacitance? If you give plus charge to one,
Sir, it will be the same method.
yeah, method is same. There's the formula will change because it's a sphere. So using the same method, can you derive the answer? The C,
Yes.
given that D is much bigger than me. And then I will tell you what is the physical meaning of this, like what is the application.
Hello.
Yes.
I got the capacitance. Is it 2 pi epsilon naught?
Hmm?
A bracket A minus D.
A minus D or D minus A?
A minus D.
You can remove the minus. You can take
Okay.
value.
D minus A upon D.
Okay. So this would be the right answer. So same method at a distance x, the electric field will be how much?
KQ by
KQ by x square
X
plus
square.
KQ by D minus x whole square.
Yes.
So now you just need to integrate. And x will go from A to D minus. So how much is this? So minus 1 by x. Minus plus. So this will become minus plus. Like this, which is like 1 by x d minus a2. We can change the sign by inverting the limits. So 1 by a minus 1 by d minus a plus 1 by a minus 1. This will repeat, right?
Yes.
2kq into 1 by a minus 1 by d minus. So d minus a, so this is d minus 2a. Okay.
Only D.
D minus a minus a, which is d minus 2a. Okay.
Okay. I think I made 5 instead. Okay. Yes.
Now, actually, d is much bigger than a, so we can compare to d. We have to ignore a. Actually. And if you do that, you get 2kq, and d is much bigger than 2, so it is d by ad. D cancels out, so what you get is 2kq by a, and the c is q by delta v, which is a by 2. The answer is 2 pi epsilon naught a is the answer. Which is pretty easy. You can do this directly without doing any of this. So what is the simple way of doing this? So what is the potential of the surface? KQ by A.
KQ by
And what
A
is here?
minus KQ.
So it is one line question. So difference is 2kq by A,
Yeah.
and therefore the C is q
Yes.
by delta. It is A by 2, which is understood. So
Yes.
either you do it with long method, or but every time we have something spherical, we should be very happy, because for a spherical object we can find the delta v directly, isn't it? Understood?
Yes.
All right. So now the real life application is, this is the actually, I mean, this idea is used in the, just if I'm trying to design something called nanotechnology. So in the nanotechnology, we need a lot of capacitors. So in fact, every carbon atom in a lattice of nanostructures will act as a tiny sphere, and the bond length will act as a d. So compared to the bond length, the A is very small. The size of the atom is really small. So bond length will be in the nanometer and the atom may be in the angstrom or even less than that. And that is why that will act as a node. So every dot in the nanostructure, every carbon atom will act as a capacitor actually. And therefore they have the capacity of holding charge, and holding charge we call it the binary 1 and binary 0. So if it is plus charge, we can call it binary 1 and minus is binary 0. So this is how we are going to develop the nanotechnology for the computers. Okay. Or you can say nanochip based on that carbon tubes. So this was the example we should be aware of. The next we need to know is something called inclined plate capacitor. So we know the parallel plate capacitor, right?
Yes.
And one of the plate we are just slightly tilting like this. This tilt is turning to 0 degree like this. But if I draw something like this, it will make no sense to you. So I have to make. So okay, I'll make it in fact like this as of now. Don't take the dimension seriously. So this is the angle theta. This is the length A. I mean the gap is A on the left side. This is L, the length. The area of the plate is A each. And because theta is very small, so area is roughly equal. If I make theta really large enough, as I have shown, the area cannot be same, isn't it? Then what we'll get is two area. Understood? So theta is kept small for the multiple reasons. The only reason is like we want to keep the so area is roughly same for both the plates. Theta is tending to, and because theta is really small, you can use the approximation binomial or whatever you know. Just okay. So given all this thing, it is filled with, or you can keep it as such. You can fill with dielectric also. So what is the capacitance of this arrangement? So now every time you are not supposed to go through the basic and derive, because even you try to apply the basics, here things will be slightly difficult to implement. So what we do is you take the clue from the parallel plate capacitor, and the parallel plate capacitor is the basis of deriving any formula that we have derived so far. Yes, every question that we have derived from the basic can be derived from the parallel plate capacitor. So what is the parallel plate capacitor formula? Let me just read this. So the property of the parallel plate capacitor is that area is same. The two plates will have similar area, and the formula for the capacitance is C equals to absolute not area of the facing plate upon separation, which is very small. We call it D. Now the question is how to convert every question into parallel plate. So what you can see in this problem that the separation will keep on changing as you move from left to right, isn't it?
Yes.
So what if I take a small piece of it? And if I call this as X and this as dx. Now the plate facing this dx, this plate and this plate, are they having similar area? Yes or no? Assuming theta is tending to 0. Imagine, first you make theta almost 0. So what you need to look for is this part. This part and this part is same, no?
Yes.
So what we say that when we make a very small part, then from left end of the plate cut to the right end of the plate cut, can we assume the separation to be almost same? Almost same.
Yes.
So what will be the area of this dx length? What is the area here? dA. Can you
Yes.
tell me the area here? How to write the area? How to express the area? In fact, in terms of AL, the area A belongs to what length? L length. For L length of plate, area is A, isn't it? For L length of plate, the area is.
A.
So what will be the area for the? So what will be the area for
dx A by L.
the? Correct. So this is what you're doing. So you're taking a tiny part of it. Now this is like a parallel plate capacitor, isn't it? And we can say dA equals to, which is the best thing you need to know first. dA equals to A by L into dx.
dx.
How many of you are able to understand this? Tell me.
Yes.
Tell me, guys.
Yes.
So if dA equals to A by L into dx, now we can write the capacitance of this tiny plate area DC. So how to write DC? Epsilon naught dA by separation.
Yes.
Can we call separation as Y?
Yes.
Now, if you go from left to right and if you take such slices, all slices will have a similar terminal, isn't it? Or you can say all slices will span from one plate to the other plate, isn't it?
Yes.
Now, what does it mean? If all plate, I mean, if all such slices will span from plate 1 to plate 2, can we say all such slices are in parallel? Because they
Yes.
have the same terminal. Okay.
Yes.
So all such plates are in parallel. So in parallel combination, what is the C equivalent? So in parallel combination, we add all the C, right?
Adding all. Yes.
We write as all DC. We add all DC, which is like epsilon naught A dA upon Y. But we must convert this into a meaningful variable to integrate. So we will pick the X. Can we express Y in terms of X? Anyone? Can we access y in terms of x? Anyone?
I'm not getting it.
Very good. I mean, the basic math, you don't know how to manipulate, how to write one thing into other. What is y? Why the separation? How to write y? Let's say if this diagram is given to you, you have to find the height y. What is the thing that you don't understand? It's mathematics. So you're not able to express anything. If this is x, I can say this is also x. How much is this? Let's call z. So we can write clearly z is how much? Tan theta equals to z by x. So z equals to, and since I'm saying theta is very small, tending to 0, so we could have done directly z theta x theta. So y I can see clearly is a plus z. That is the meaning of writing in suitable variable. Is this clear now? Is this clear?
Yes.
So we can write absolutely not, and dA we can rewrite as a by L into dx, and y is how much?
A plus x theta.
So now you can clearly see that absolutely not a upon L, we can take it out, and what we are left with is a plus x theta, and the x will vary from where to where? Can you tell me? X will vary from where to where? To cover the entire capacitor, I must take the x from where to where? To cover the entire capacitor, every slice I need to take in the entire plate area. How the x must vary? Okay, it will vary from 0 to L. Is it okay? So x0 means you are at the leftmost end, and xl means you are at the rightmost end. So the slice which I have taken will vary from here to here. Understood?
Yeah.
Is this clear, guys?
Yes.
What happened to all? I mean, you're not able to answer a single basic mathematical thing. We have been doing this for years. I mean, I don't want to discourage anyone. But with this kind of preparation, I doubt anyone will qualify. So ramp up your basic understanding of math, then physics will make sense to you. Anyway, so this will become epsilon not a by L, and the dx upon a plus x theta will be how much? Tell me. Okay, you don't know the integration.
Log of a plus x theta.
And after putting the
So
limit,
from L, no, then L to 0. So, yes.
okay, so you all practice. You all go home today and just grind yourself and ask. I mean, stand in front of me if you want to qualify JEE. What it takes? Does it take not answering any question and not knowing the basic geometry, trigonometry, basic integration, differentiation? So if you think that without knowing any of these, if it is easy to qualify, then come out of this myth. You have to work hard. You have to do the derivation. So everyone at home, you go and practice all the derivation of entire electrostatics and capacitor so far. Just like just I am doing, you're watching it. So anyway, all those lectures I'll put on the YouTube, you just watch it there. Why to come here? Okay. So the answer we got is how much? C equivalent is how much? Option not A by L. Ln A plus L theta by A, right? This is what we got.
Yes.
And this we can write as okay. Now this is something interesting to understand, that we can use the, this we can rewrite as 1 plus L theta by A. Okay. And theta is very small, so although L is big a value, but theta is very small. So L theta is very small, so we have the expansion relation from ln of 1 plus x. And how we write is x. I think all plus, no? Or is it alternative? Just,
Plus.
just I think all plus.
Plus.
No, I think just check. Ln of 1 plus x. It is alternate plus minus.
Alternate.
Yeah, alternate. Is it alternate? Alternate plus minus?
Yeah, sir. Alternate plus.
Yeah. So for this case, we can write this as, we'll take the two terms, or in fact, we can take just only one term. So because x is very small, so x square will be even smaller. So for approximation, what we must remember, that ln 1 plus x we can just write as x. And therefore the C equivalent will become epsilon naught A by L. And this is L theta by A. Correct?
Yes.
So this is epsilon naught A theta by A. Okay. So if I want to know what is the change in capacitance from the parallel plate to, if you tilt by theta, how much capacitance will change? So we know that epsilon naught A by D, and A is the D when before tilting, right? This is like a D.
Yes.
So you can clearly see that delta C is basically epsilon naught A by A minus epsilon naught A theta by A. So this is the change in capacitance that you will see. Understood?
Yes.
Okay. Anything. So they may ask you what is the new capacitance before the tilt has happened. So the separation was A in the beginning, then you tilt slightly on the other end. And then how much capacitance will change? So it will change proportional theta. And if it is only when it is very small. Okay. Okay. So what next we can do? Again, this is for the record, we need to teach this, although it's not required. It's like again the challenging one. So this was asked by the IIT-JEE in 1987. Imagine how old the problem is. So in this problem, the plate between the capacitor is divided into two dielectric. So the top one is filled with some sort of dielectric, and the bottom is filled with dielectric like this. So like it's like a two sandwich, yeah, stacked together. And the plates are basically the green one. So now the upper one, let's say having the dielectric constant K1 and the lower one is having dielectric constant K2. Okay. The separation is D as usual. Area is A, and the length you can take as A. So length, it means A. You can also find the width if you want. So width is basically A by L. You can think this way. So they will either give you length and width separately, then they will not give you area, or what they can do is they can give you area and length, not the width. But anyway, you know the length and width is equals to area, right? So the question is, what is the C equivalent? So I'm giving you, let's say, 5 minutes to think about it. Then we'll discuss that what you thought about. And then I'll solve. Take your 5 minutes, think about it. Think of the approach. No need to solve it. Just think of the approach.
Hello.
Yes.
Then we will do it by the inclined plane concept
No, nothing like that.
because
No, nothing like that. You have to do it by the parallel plate capacitor itself.
Okay.
Here we have two dielectrics. So if I take a slice of it, this slice will have two capacitor, two dielectric in series, right? If the slice is really small,
yes.
you can see clearly there are two dielectrics. One is K1 and then a small part is K2, right?
Yeah.
And these two are in series. Understood? So if this is X and if this is dx, which is really small I have drawn, what you can realize that if I choose this as Y, if I choose this height as Y, the other height becomes D minus Y, right?
Yes.
So I can say the elementary capacitance of this entire dielectric capacitor of thickness dx itself will have two series combination. So the 1 by dc becomes 1 by dc1 plus 1 by dc2. Do you realize this?
I didn't get it.
So dc1 is what? The from here to here, like this part,
Yes.
and this is dc2,
And
they are in series
yes.
combination.
Yes. Good.
So for series combination, how we write 1 by c equivalent is 1 by c1 plus 1 by c2. Now how to write dc1? Epsilon naught k, first of all k. What is k here? K1 epsilon naught, right along with me. Now what is area? What is the area in terms of A, L, and dx?
A by L dx.
And what is the length, like d?
D minus Y.
Very good. So similarly, what is dc2?
K2 epsilon naught A by L dx upon Y.
Okay.
Yes.
So first step is you substitute the value in the formula on the left, simplify, take something common, and then whatever you get the answer, convert y into x first or x into y. So what is the xy relation? So you can say tan theta equals to, suppose this is theta. So tan theta we can write as y by x, which is d by l, isn't it?
D by L.
So sometimes we can differentiate like this also. So what you can do is first solve, write the answer, and replace dx in terms of dy. And then integrate the y from where to where? 0 to d.
0 to
D.
yes.
So these are the steps that you have to take to solve this question. So I'm leaving the remaining part as a homework. Okay.
Yes.
And this is also the answer given in the SC Verma last question you can see. This is the last question of SC Verma in capacitor. Okay.
Yes. Sir.
All right. So we'll see the rest in the next lecture. Bye and take care.
Bye. Sir.
Bye, sir.
Everyone do revise. I can see you guys are not revising, which is not good for you also. So this is a difficult chapter, I know, but what I'm saying is only with hard work you can make it easy. My ability to make easy is over. So this is calculation intensive chapter. You have to work hard. Accept it. You will be at ease. Else,